I'd like to talk to you about board games, tabletop games. I'd like you to picture with me that you've sat down to play a tabletop game with a friend. And you're playing the game, but the game state gets a little hard, a little complicated. In fact, you're not quite sure, it seems to be so complicated that you're not quite sure whether the game is stuck in an infinite loop or not. Is this game ever going to end? You've just got these things set up so it looks like they might not ever end. So you go, okay, you know what I'm going to do? I'm going to take this whole game state and input it into my friendly computer. And then the computer can analyse the game state of this tabletop board game and tell me whether this game is actually winnable or whether it's stuck in an infinite loop. But it turns out that the computer can't tell you that either. It's mathematically proven that this tabletop board game, no algorithm can look at any game state and tell you whether this game is going to terminate or not. You might think that's going to have to be a pretty unusual game. That's not going to be the kind of game that people play on a regular basis. Well, it turns out that in a very popular tabletop game played by hundreds of thousands of people around the world, this is exactly what happens. My name's Alex Churchill, and I'm here to talk to you about how we prove that Magic the Gathering is Turing complete. So let's start by talking about some other tabletop games. Chess. We like talking about chess here at Fun, don't we? So what's the computational complexity of chess? Does anyone know?
It's the XP time complete.
X time complete. At least that is if you generalise it to an n-by-n board, right? I mean, obviously that's the only way the question makes sense. What about the actual 8x8 game, the way people sit down to play chess?
Constant time.
Constant time. You can brute force it. There's what, a few decillion game states, it's nothing much, right? Go. What about, it's the same deal with Go. It's X time complete, there's a couple of Google squared game states, maybe the square of that number of game trees. Can any tabletop game be actually computationally complex without generalising it to an n-by-n board? If you take the game the way it is played. Yeah?
Yes, because you're asking this question.
I like the way you think so. Yes, so I mean, the literature before our paper has, one or two. Dots and Boxes is a game that it doesn't inherently have a fixed board size, and the literature's got some interesting results of Dots and Boxes. Amusingly, Jenga, the game where you stack the blocks, although your Jenga set that you buy from a shop, again, that's going to have a fixed number of wooden blocks. You can't really scale it to millions. So let me tell you, just ask the question, how do you show a tabletop game is Turing complete? What are the ways that you could do this? Now, if you were showing this for a computer game, then I think the way that it's been done in a number of fun type papers is you establish some computational logic framework, some way to build wires and gates and that kind of thing. And it may well be that there's some tabletop game where that can work, but the way we chose to do it is build a universal Turing machine inside Magic the Gathering. And as I said before, most investigations of this type have considered extensions of standard games like chess on an infinite board. This may be, we believe, the only result to show Turing completeness of a popular tabletop game following all the rules, the way they are played by people playing the game in the normal world. So let me tell you a little bit about Magic the Gathering. Who here knows anything about Magic? Who's played it a little bit? Yeah, half of you, third of you. So yeah, it was the first collectible card game. It was first published in 1993, and they keep coming out with new cards. This company called Wizards of the Coast publish it. Players will have their own collection, maybe thousands of cards. You'll shuffle them up. You'll select a certain deck. You'll choose your own set of 60 cards that you think work well together with each other. And then you'll take that deck along to meet up with someone else, and they'll bring their own deck.
Is there a finite number of cards?
There is a finite number of cards. Wizards of the Coast have printed about 20,000 different cards, but yeah, your deck can only be composed of the cards that Wizards of the Coast have officially printed, And generally decks are 60 cards. You are allowed to bring more than that, but limited by practicality. You can't ask someone to bring in 1 million cards because they have to shuffle the deck. So, if you wanted to build a Turing machine inside any system, then what are the things you need? You need a tape, you need a read head that can look at the current symbol on the tape, you need some rules, some way for it to apply rules, to write a new value to this cell and to move left or right, and some way to change state. That's just the definition of a Turing machine. But even if we could embed a Turing machine into Magic the Gathering, that doesn't necessarily prove anything interesting, because not every Turing machine is universal. So there's a guy called Yuri Rogozhin, who, I probably pronounced his name wrong, who did some fantastic investigation into very small universal Turing machines by embedding something called a two-tag system into them. And this is a great graph by Neary and Woods showing the number of states that your Turing machine needs to have and the number of symbols your Turing machine needs to have in order for it to be powerful enough to be universal, to embed any computation into it. And so one possible place that we might try to build a Turing machine inside Magic the Gathering would be with 5 different symbols, 5 different things, because Magic the Gathering has 5 colours in it. And it turns out that to do that, to make a universal Turing machine with 5 symbols, you also need 5 states. Making states in Magic the Gathering is really hard, it turns out. So instead we went for the 218 universal Turing machine. If you limit yourself to just 2 states, your Turing head can be in either state A or state B, but that's all, then you need 18 different symbols to make a universal Turing machine, but that turns out to be enough. And so I'm just going to show you a few of the magic cards that we used to assemble this, and these are all cards that are printed by Wizards of the Coast. So Magic the Gathering has one ability called phasing, which is a really old, obscure ability. They were only printing it for less than a year, but it does exist. Some cards might have the text phasing on them. What this means is that they disappear and then reappear. Every turn they're treated as though they don't exist, and then the next turn they're treated as though they do exist. And some creatures are printed with this ability on them. They're not very interesting, but crucially, there is a card that you can attach to another card and say, the enchanted creature, you're enchanted with this card saying, this creature over here has phasing. And so every turn it will cease to exist and then start to exist again. So I'm just going to show you a couple of things about magic cards. So there's, like I say, about 20,000 printed cards. When people play a card in Magic, either it will take its effect and go into the discard pile, or it will stick around in play on what we call the battlefield. So here's some examples. Cards can have colour. These examples are red, green and white. They can also be black and blue, but that's it. 5 is the number of colours you get. You can't make up any more. There's no such thing as pink or purple cards in Magic. These are examples of creature cards. And creatures have this thing down at the bottom corner that is their power and toughness. You can think of it as their attack strength and their hit points. How much damage they deal in combat, which is not relevant for our purposes, and their life, how much damage they need to receive before they die, and that is relevant for our construction. So we've got a 5-5 here, and a 1-3 and a 4-4. So they've got toughness, health of 5, 3, 4. And they've also got creature types printed on this centre bar here. So we've got a dragon, we've got an elf druid, we've got an angel. And there are a few hundred creature types printed on Magic the Gathering cards. These are spread across all sorts of different mythologies, because the game's been running for 30 years. It's visited a number of different mythological settings and assembled a lot of its own lore. But still, we have the fundamental problem that if a Turing machine needs an infinite tape, or at least an arbitrarily long tape, and you can't ask someone to shuffle a deck of millions of cards, what do you do? Fortunately, Magic the Gathering, in common with several other games, has the ability to create what it's called tokens. So here's a card that's very simple. It says, create 2 1/1 red goblin creature tokens. And this is one card, but when a player plays it, they'll end up with 2 things on the table, 2 creatures on the table. And these are creatures. They have colour, power and toughness, and creature types. But when people are playing the game face to face, they might use, beads or pens. But there do exist also these printed tokens that Wizards of the Coast supply. And you're allowed to use anything convenient to represent them. People might use dice to represent them. Now, one of the most crucial capabilities that Magic the Gathering has to allow this to exist is that you can edit the text of cards using other cards. This one card, Artificial Evolution, is more key to our combo than anything else. It says change the text of target spell or permanent, that means any one other card, by replacing all instances of one creature type with another. And the new type can't be legend or war. So you have to choose another creature type that's existing inside Magic, but there's a few hundred of those, and you can change something that would have made zombie tokens to instead make Pegasus tokens. Yes?
Can you apply it to itself to change legend to something else and then change something to legend?
It's actually, you could do that with war, yes. You could put this on the stack and then cast another copy of it targeting itself to change the word war. If you really wanted to make something war, yes you could. Likewise, there are other cards that will allow you to edit colour words in printed cards. So you can take something that would have created black zombie tokens and use glamour dye to change it so that it creates white zombie tokens. And there's cards like Prismatic Lace that allow you to edit the colours of other cards as well. And these cards are absolutely crucial to our construction. And Magic's been running, like I say, since 1993. Artificial Evolution was printed in 2002, I think. If you had to ask me, what was the time when Magic the Gathering became Turing complete? My best guess is it's when that card, Artificial Evolution, was printed. The designers, when printing it, knew that they were allowing some interesting combos, players to create some fun things. I don't think they had this in mind, but...
What's the price of this card?
It's a cheap one. Yeah, I'm sure you could pick some up for a pound or less, a euro or less. So, like I say, we need, if we're going to use phasing to represent the two different states of the Turing machine, that means we need 18 different symbols. Fortunately, Magic the Gathering has a nice long list of creature types that it supports. There have to be. You're not allowed to make up your own creature type. It has to be one off the list. Advisor, Etherborn, Ally, Angel, Antler, all the way down to Yeti, Zombie, or Zubra. There's enough there for us to work with. So, we chose 18 different creature types, beginning with successive letters of the alphabet. I like to imagine this as baby's nerdiest alphabet book. A is for Ethan, B is for Basilisk, This screenshot is taken from a video created by a guy called Jan Beal, who's excellent, who he looked into how to convert an arbitrary Turing machine program into something written in our Turing machine. So, to create the Turing lead hack, we need to specify what happens when a particular symbol is read from the tape. And since we're going to be writing a new symbol into that tape, and Magic the Gathering is a game about combat, it turns out to be convenient to represent this by killing the creature that represents the current symbol on the tape. And then there's this card called Rotlung Reanimator, which has printed, says whenever Rotlung Reanimator or another cleric dies, is put into a graveyard for play, create a 2/2 black zombie creature token. That is like one rule, one piece of data from the program. So the first line of the program says, whenever we read symbol A, we want to write symbol 18, symbol S, and move left. So we cast 2 copies of Artificial Evolution and 1 copy of Glamour Die to edit the text of Rotlung Reanimator. So now it says, whenever Rotlung Reanimator or another Etherborn is put into a graveyard for play, we create a 2/2 white sliver token. And we can go on working our way through the program, making lots of token copies of Rotlung Reanimator, attaching this enchantment to give them all phasing, and encode the full rules to all the to both states of the 218 Universal Turing machine. Each of them will notice a particular creature type dying and create a new creature type, and it will be white or green according to whether we want to move left or right on the tape. But wait a minute, left, right, these are not concepts that exist in Magic the Gathering. The other real big challenge to making this is Magic has no concept of dimension, no proximity, no geography. A number of tabletop games do, but there's nothing like that here. And so we needed to assemble the concept of dimension. And we do that by using tokens. So there's a number of ways in Magic to do things like put a +1/+1 counter on each creature, which is going to increase their power and toughness permanently, or put a -1/-1 counter on each creature that will decrease their power and toughness permanently. And so if you imagine that we've got a set of tokens, a 1/1, a 2/2, and a 3/3, and we cast a spell that puts a +1 counter on each of them, then they become a 2/2 and a 3/3 and a 4/4. And there's no geography or proximity here, they could be in any position on the table. But if we then put a -1 counter on each of them, then we'll move back the other way. And so we end up with this system where we've got a series of green creature tokens that get larger the further away they are from the Turing head to the left, and a series of white creature tokens that get larger the further away they are to the right. And the operation of moving the head left consists of putting a -1/-1 counter on all the green creatures and a +1 counter on all the white creatures. And we can rephrase that as we put a -1 counter on all creatures, which is exactly the text of all the cards I showed you, and put two +1/+1 counters on every white creature. There isn't actually a printed card that do that, but we can assemble a few different cards. You'll have to check the paper for full details. So, we have everything we need. We've got a tape, 2 series of green and white creature tokens, we've got a read head, lots of rotten reanimators with edited text. We can move left or right by putting counters on creatures, and we can change state using phasing. So the interesting thing about this is all in the game as played. We then wanted to remove all player choices. So this turns out to actually be fairly easy. Magic the Gathering likes printing cards that remove choices from your opponent. So we can remove all the other cards, we can remove all the cards from the opponent's hand so they can't do anything. We can stop players using their mana, using choke, we can stop creatures attacking. We need to force people to do the same thing over and over. That's actually harder. There's not very many cards printed that will do that, but the way we do it is using wild evocation, which each turn forces a player to select a random card from amongst the cards in their hand, so we make it so they've only got one, and then they must play it if able. And this card called Wheel of Sun and Moon, that means when you play a card, it doesn't go into your discard pile, it goes on the bottom of your deck. And so with those two in play, we've removed all player choice. We've removed all player actions. The players have no options remaining, except to just do what the cards force them to do, cast the same series of cards over and over again. Infest will kill the current creature, triggering the creation of a new creature token. Cleansing Bead will put some +1 counters on something. Coalition Victory will check whether we've halted or not, and Soul Snuffers will put some -1 counters on something. Round and round and round again. Looping millions and millions of times. Is it infinite? Well, that depends what you've set up the computation to compute. Maybe this game has been, when you set up the tape, you set it up so that this game will terminate if the computation finds a pair of twin primes greater than 1,000,000. And the interesting thing about this is this fits the way the game is normally played. I mean, by which I don't mean that people set up Turing machines in games regularly, but you could take this deck, sit down in a regular tournament, and if you get just the right draw, I think that happens about 1 in every 50,000 games or so, then you get to take over the game and remove all the opponent's choices. And I mean, at that point you could win, but you know, where's the fun in that? Instead, let's set up something so that when the head judge comes over and says, "Excuse me, is this game ever going to terminate?" You're like, "Well, funny you should ask that. There's a thing called the halting prop." So yeah, the implications of this for a tabletop game as it's normally played are really interesting. In a typical game of Magic, you can't tell whether this game is winnable with optimal play, you can't tell whether it's going to finish, whether you're stuck in an infinite loop or not. And okay, there's a caveat there. At least no computer can do that for every game state. Obviously, most game states are actually rather more tractable. You can easily tell whether someone's going to win. But nonetheless, the fact that there exists an algorithm that will show that this is never going to be possible in every state. So I wanted to just finish by mentioning a couple of people who've made some YouTube videos about this. There's a guy called Kyle Hill. who actually built the Turing machine in real life. He really wanted to see what it looked like. So he shuffled up this deck, well, he didn't shuffle it, he arranged so that he drew the right hand and set it out. If you search YouTube for Because Science Magic or Magic Turing Complete, you'll see this. He also drew a picture of me using blackboard markers, which is unexplained but flattering. This guy called Jan Biel then created a compiler, a sequence of steps that will take any Turing machine set up to compute something helpful, something sensible, and turn it down into a two-tag system and then into the universal Turing machine. The compiler is not particularly efficient. It turns out to need about 40 million tokens if you're trying to compute 2 plus 3. Trillions of game operations, but nonetheless, it is possible. If you search YouTube for Magic Turing Machine compiler, you'll find that one. And yeah, the open question is, what other tabletop games could be Turing complete? My hunch is there aren't any. It's going to be really hard. You need certainly no limit on the number of player actions or triggers that could come up. You need a way to store arbitrarily large numbers, preferably arbitrarily many of them. Otherwise, you're going to need to get into some tricky stuff with Gödel numbering. You need a way to constrain player choices, and even more than that, you are almost certainly going to need some equivalent to artificial evolution to edit the text of other cards, or at least customize what cards or game actions trigger other game actions. So yes, I'd like to thank me and my collaborators. We'd like to thank Chung-Min Hu at HAL for some fantastic simplifications, our friends Edwin and Jack for early suggestions and ideas that led to this, and thank you for listening. Any questions?
We can take a couple of questions.
Yeah.
So I was curious, when did you start thinking of, maybe I could actually prove magic to be Turing complete?
Somebody asked the question, like back in 2015 or so. I've been working on it for several years. You might have seen some early results along these lines several years back. It was only in 2019 that me and my collaborators managed to actually formalize it, remove all player choice. And then, in 2019 was when those videos were made, and then the paper was accepted for 2020. But yeah, I've been working on it for almost 10 years.
Other questions?
How much is the Turing deck?
How much would it cost to buy this deck?
All the 460 cards.
So it turns out that the actual cards that we use for the combo are super cheap. Nobody wants Rottlang Reanimator and Artificial Evolution. If you want to include some cards that will let you take over the game on the first turn and get enough mana to draw your entire deck on the first turn, those are the pricey cards. So yes, this is not actually a real ancient tomb. This is a proxy that one of my friends printed for me. Because the real one is about $200 and we want 4 of them in the deck.
Okay, thanks a lot.
Thank you.